right? So transitivity, right? So suppose we have x, if x is equivalent to y, then we know that we have gamma from 0, 1 to our topological space, big X, such that what? Gamma of 0 is x, and gamma of 1 is y. So to prove that y is equivalent to x, what do I have to give you? I need to construct beta from 0 to 1 to x by beta of s, let's say, equal to gamma of 1 minus s. This is the reversal of the curve. Not a popular topic with my Calculus 2 this semester, I will tell you. What's that? I talked about, no, I'm doing Calc 2. I talked about reversals of paths in there. Mistake. I already removed it from the test. I'm not even going to try. No. It's a loss. It didn't go well in lecture. Just bad planning on my part. You can check. Beta of 0, gamma of 1. Beta of 1, gamma of 0. Why is beta continuous? Because it's the composite of continuous functions. Because 1 minus s is a continuous function on the rails. S maps to 1 minus s is continuous, right? You agree? I hope you agree. That's a continuous function. Now, transitivity, though, that's a little bit, that's harder, right? Suppose you have x equivalent to y and y equivalent to x. What do you want to do? You draw a picture to organize your thinking, right? It's like, why is King frowning? Oh, okay. Yeah. Oops. Didn't mean to drop it. So call that gamma 1, call that gamma 2. So what we need to do is build our gamma of t to be what? Something like gamma 1 of 2t. What that will do is it will speed along here. So it's going to like double the speed, like, and then we want to go double speed on this one too. So this is for 0 less than or equal to t less than or equal to 1/2. And then we do gamma 2 of t. Well, what do we put there? Yeah, 2 times. Do I put t minus 1/2? Minus 1 like that?
No, I mean 2t and then minus 1.
Give me the formula. What do you want?
2t.
2t.
And then minus 1. No parentheses.
Just like that.
I mean, you're saying 2 times t minus 1/2 is fine.
It's okay. I don't need to be right. I just want something right on the board. Those are definitely continuous, and I believe they glue together, which means that there's a gluing lemma for gluing continuous functions together. We might talk about that someday. And there you go. That proves that x, that's a path from x to z, so then x is equivalent to z if x is equivalent to y and y is equivalent to z, right? So what this proves is that path equivalence is an equivalence relation, and then we can take the equivalence class of this relation, and those are what are called path components, right? So you can look at the path components of a space, and those will also partition the space. And path connectedness implies connectedness. All right. As he says here, theorem 9.2, a path-connected space is connected. All right? And he has corollary 9.3. Each connected component of X is a union of path components of X. So the connected components don't have to match the path components, but they're at least a union of path components. That's hard for me to visualize, but it is what it is. Now, exercise 7 shows you that there's an inequivalence between path connectedness and connectedness. So this is a very famous, it's pretty much the only example anybody ever gives. I'll try to talk about it for a second here. This is the so-called Topologist sine curve, I believe. So he says let E 0y such that minus 1 less than or equal to y less than or equal to 1. So, and then f equal to x, and then sine of 1 over x, such that 0 less than x less than or equal to 1. And he says let x be the union of those two guys. All right. He claims it's compact. Well, wait a minute. I think he's claiming that E is compact. I mean, yeah. No, I think he's saying X is compact. He says, show that X is connected but not path connected. What are the path components of X? So here's a picture of X. I hate to ruin this marker. I forget where it ends up. Sine of 1, right? Wherever that is, I don't know. So I think there are two path components. The two path components are E and F. Because you can't get from one to the other without the path being discontinuous. I believe that's the problem. Like if you tried to go from here to here, that's not going to be continuous because of the way that the graph is bunching up. I'm giving you a heuristic argument. You'd actually have to flesh it out. It'd be harder, but this is the example. It is nevertheless connected. Like you can't find a separation of X. I can't think about this too much. It breaks my brain. But most of the examples that I'm interested in happen to be path connected. So for me, the notion of path connectedness is usually the one I like to think about. For example, a manifold is path connected. Locally path. Thank you. Locally path connected. Yeah, this is true. It doesn't have. It could be. You're right. You're right. Locally path connected, I should say. What does locally path connected mean? Something to do with neighborhoods, right? Right. That seems safe to say. A nice test question is to prove, and I don't want you to, from the definition alone, all right, prove that the union of path-connected spaces is path-connected, as long as it has So suppose you have two path-connected subsets of a topological space, all right? And their intersection is non-empty. Can you prove that that union's path-connected? How do you do it? I mean, I can draw a picture to explain that, right? So here's my two path-connected spaces, right? If you take any pair of points in either space alone, of course, there's a path connecting by assumption, right? So the interesting case is to take a pair of points where one is in one and one's the other, right? So suppose you have x0 here and x1 over here. And let's say this is x and this is y. And x intersect y is non-empty. And I'm assuming x and y are path connected, right? So the proof is very simple, yeah? Since it's non-empty, that means that there's a point in the intersection, right? At least one. In this picture, it could be less than this. Like the picture could really just be just touching at one point. Like that could be it. Just takes one point, because that one point is all it takes, because we can always connect this path over to z, and then take that and connect that over to that. And if you join these two paths together, right, then you get a path from x0 to x1. The join of two paths we used in the proof of the transitivity of the similarity, the equivalence relation of the path, the points. That thing we did with doubling the speed, that's the join of two paths. Yeah, or you could use, exactly, yes. Fair enough. We did prove it. We could use it, I guess. Fair. Yeah, you got me. I'm trying to say is I could see you guys finding a more convoluted theoretical way of proving it, right? Like, well, path connected implies connected. So I'm looking at the union of two connected spaces whose intersection is non-empty. We already proved earlier today that that's connected, so therefore it's connected. But what did I want you to prove? I wanted you to prove that the union of the two was what? Path connected. So that actually wouldn't do it. My fear was irrelevant. I would like you to, it's good if you learn theorems. Don't be like me. Don't forget everything. Yep.
Just for simplicity's sake, can we define a path to be like continuous mapping from any closed interval on the reals to the space? That way you don't have to go through the whole 2t from 0 to 1 half type thing.
Well, you could prove a lemma that if there's a path from A to B, A less than B, that implies that there exists a path from 0 to 1, and then you could use that lemma, I suppose. But you're right. I mean, different books might use different definitions there. That's mainly a convenience for proofs. I think everybody knows that you could replace 0, 1 with something else. Sometimes people take the domain to be the whole reals. That makes me a little bit nervous. I don't know why, but anyway. Well, I tried, guys. I think that's where we got to. In terms of test 1, there's some bits and pieces I've missed. Like an important thing I should have said in class and would have been good for us to dig into was, why is it that the limit of a sequence, did I prove this? I don't know. The limit of a sequence is unique in the context of what? What makes limits unique for a sequence? T1 space, but Hausdorff is what I was after. Definitely Hausdorff implies that the limit of a sequence is unique. So that's an important thing to know about. And I don't think that's to say that that's the, I don't think that's minimal. I mean, I think you could strip away. I think that's still, T1. T1 is the bare bones. We could the.
Well, actually, there's a subset which should be minimal.
So you think there's something called R0, which is the smallest bit of the weakest conditions we could impose and still maintain uniqueness of the limit?
Yeah,
T0 is Kolmogorov. Ah, interesting. Huh.
T0 is not.
I'm not trying to say that's going to be a test question or anything. I'm just saying that's something that's of interest. Yeah. So, listen, guys, just do your best. Like, don't like stress too much. Just do your best on the test, and it'll be okay.
And the test is the Monday following this Monday?
Whenever I said,
I think it's the 18th to 20th.
right.
Are we just taking it in the testing center?
No, it was somewhere around here. I don't know how to send stuff to the testing center. We don't want to scare them with the topology test either, right? Are there any? I'll turn this off. So